Hello and welcome to this tutorial on dealing with character data in R. My name is Wouter van Attenveld, Vrije Universiteit in Amsterdam, and you can go to my website at vanattenveld.com/r. If you want to follow along this tutorial, just follow the link to our GitHub page with all the course materials. And this is the tutorial on basic string handling. So if you follow along this tutorial, it should contain all the code that I'm using in this example and some extra explanations around the codes. What I want to talk about today is first a brief note on the difference between the various data types, especially the difference between strings and vectors. Then I'll talk about some basic functions to manipulate strings in R. Then the important topic of regular expressions, and finally a very brief note about character encodings. First, about data types. So as you know, of course, every element in R has a data type. And for example, if we have numbers, like here, then we can ask for the class of this object with class X, and that shows us that this is a numeric object. If we are dealing with text, the main data type is of course the character. So suppose we have a vector of three names, then this will be of class character. It is quite easy to convert between two classes. If we go back to our numeric, we can easily convert this to a textual representation with as character. We could also convert a textual representation back to a numeric representation, but of course in this case it won't really give us anything because there is no numeric representation for Pete or John. If instead we would have a number encoded as a text, like the number 12 between quotation marks, this is still a character, this is textual data, but we can now convert it safely to a number. If we have a mixed set like this, then it will convert them to numbers. It will convert everything it can't convert. It sets us to NA, to missing value, and it will give a little warning message here. Now, there is another data type that you might encounter, and that is the vector. And a vector is basically how grouping variables are represented. So if you have a nominal variable, so maybe you have three groups or whatever, three conditions, which is a nominal variable that is ideally encoded as a vector. And with a vector, you have the values like Pete, John, and Pete here, and it also has two levels. Internally, actually, this is encoded as a number. So if you ask a numeric value of this, this is 2, 1, 2, because Pete is the second vector and John is the first vector. And the ordering here is alphabetical, and that is actually why in ggplot, if you have a legend, it's ordered by default in alphabetical order, because ggplot treats categorical data as a vector. Now, it used to be the case that if you would make a data frame containing, for example, a set of names like this, then R used to actually encode this as a vector. This changed, however, in version 4, so now everything is encoded as a character by default, which is probably a good thing. You can still do it like this, and then it will tell you that it is a vector. And if you omit this or you set it to false, then it is a character. Now, as I said, we are now at version 4.0.2 or something. This was just released a couple months ago, if I'm correct. And before that version, the default for the built-in data frame used to be a vector. This made a lot of sense when memory was expensive, and it was good to store things like this as numbers rather than as strings, especially you have a couple hundred or a couple thousand of them. But nowadays with modern computers, it doesn't really matter anymore. And it can become quite confusing if you think you're dealing with textual data, but it's actually represented as a number internally. I'll give a short example of that later. But what's important to remember now is that if you have a modern R version, it should by default give you characters. If you have an older R version, it should by default give you vectors. You can always check what it is, right, with the class commands. And if it happens to be a vector and you want to change it to a character, you can simply say mutate X so that the names becomes the S character of the names. And after this, I should have probably entered a library tidyverse somewhere here. So let's do that now, because as you know, I'm totally addicted to tidyverse. And here we go. Pete, John, and Pete is now a character, right? So if it is a vector, you can convert it with as character, and of course you can also convert it back with as vector. What is also important to know is that the tibble function, so the tidyverse alternative to the data frame, has always been default to have strings as character data. So an older version of R, one of the advantages of using tables would be that you never had to deal with vectors unless you wanted to. As of version 4.0, the two are now the same, and the base R uses the same convention as the tidyverse functions. So let me give you one small example of why it can be confusing sometimes to have vectors. And I gave you earlier the example of, say if you have two numbers like 18 and 12, you can simply convert them into a numeric value using as numeric x. And you get the result that you expect, namely 18 and 12. Now suppose that you had a vector consisting of those same numbers, right? So we have a vector consisting of 18 and 12, it looks the same. But if we convert this into numeric, what we get instead is not 18 and 12, but what we get instead is the internal representation, namely 2 and 1. Yeah? And if you're not aware that your data actually contains vectors, then you might be very surprised by these results. Of course, a very quick workaround is to convert to character before you convert to numeric, and then you will still get the same results. So anyway, the important thing here to remember is that in R, every variable has a data type. You can convert data types with as numeric, as vector, as character, etc. The default representation of character data is the character class. That's the default representation of textual data. And that's probably the representation you want to do, especially if you want to do actual text analysis. Sometimes you have vectors rather than character data. That's intended in the case of ggplot because it interprets categorical values as vectors. But in some cases you have them without realizing you have them, possibly because you use an older version of R where the default for data frames was to convert all textual material to vectors. In that case, it's important to be aware of the difference between vectors and characters to know that you can inspect which of them you have, and you can easily convert between one and the other by just using as character or as vector. Now we know how textual data is represented. Let's have a look at how we can deal with it. And we look at two things, namely normal string functions and regular expressions. We start with the normal string functions. All the functions we're using are from the package stringer, which is part of the tidyverse, so you don't have to import it again after you've already said library tidyverse. You don't have to say library stringer, you can just use the functions immediately, and all of them start with str underscore. So if you want to see what functions are available, just type str underscore and then you get a complete list of all the functions that are there. A lot of them probably make sense, like string match, string locate, and one tries to find a match, this tries to find the location of the match, this will give you the length of a string, etc, etc. All these functions, as it also says here in the explanation. Yeah, I got a beautiful explanation a second ago. Yeah. So it will generally tell you that it is vectorized over the string, and it might also be vectorized over the pattern. What they mean there is that string length is not called on a single string, it's actually called on a vector of strings, a vector of character, like most functions in R. So if you have, we have three names in there, so Pete, John, and Pete again, right? Then the string length of x equals 4, 4, 4, because Pete, John, and Pete are all 4. That's a bit boring. So let's call this guy Jonathan. And then it's 4, 8, and 4. So string length gives you the length of all these strings in your vector. Another important one is string C. String C actually concatenates strings. So suppose we have Pete and John, and we have 18. Sorry, I'm missing a parenthesis here. And then it concatenates the values here with the concatenates over there. So this is the string concatenation function. So by default, it takes every element from the first set, every element from the second set, etc., and it combines them all. If you would have two values here, like we have 12 and 18, and then it would do P12 and John 18. So if you have multiple values, it combines them one by one. If you have only a single value, this value is used for all of the values on the left. By default, strc, the string concatenation, doesn't put anything in between them. You can put something in between them if you use the separator. So if I put a space here, it says Pete space 12 or John space 18. So one use for this could be, for example, if we have to get a lot of data from this website, then you could say the base URL equals this, and then you can say the URL is concatenate. On the base URL we have, for example, the file.csv, right? And then it will create a new character consisting of the base and the file.csv. So this is one example use case. What you possibly saw when I asked for the help, you can have both the separator and the collapse. The separator is what it puts in between the various arguments of the function. The collapse is actually used to collapse all the arguments, all the elements in the first argument to a single string. So if I would say collapse equals like a underscore, then it creates a, sorry, that should have been string C. Then it creates a single string, Pete, Jonathan Pete, with a little underscore here, right? So with strc, you can both combine multiple separate textual objects, so multiple separate character vectors, or you can collapse a single character value, single character vector into itself. You might have noticed that this is actually quite similar to the built-in paste function. Actually, as far as I know, it's completely similar to the built-in paste 0 function. The only difference with the paste function is that by default, the paste function, if you have John and Mary, will put a space in between, while the paste 0 function doesn't put anything in between, but the strc function behaves the same as the paste 0 function and doesn't put anything in between. Also with the paste function, you can have the same arguments like the separator and the collapse. So there isn't really any difference here, but if you're using the tidyverse functions anyway, you might as well also use the tidyverse function here. A final useful function is the str sub function. Suppose we have a set of dates, and these dates in ISO notation, they start with the year, month, date, and then they might have a t and the time, or they might have a space in the time, or could be more complicated anyway. Suppose we are only interested in the date part, which is the first 10 digits, the first 10 characters. Then what we can do is use the subset function on the dates. We start from the first character and we end on the 10th character. And then it just takes the subset of the first 10 characters. Of course, we could also take the subset of the last. We can use this to pick any substring from a string. And again, as you see, this is vectorized on its argument, so it will automatically take the first 10 characters of every element of data. Now there are lots of more functions, and as I said, you can just use the str underscore and then have a look at all of them. Another great source of inspiration here is actually the RStudio cheat sheets, which they have for a lot of different things that you can do. So if you just Google for RStudio cheat sheets, you will find a list of all the various cheat sheets, and they have one actually on Stringer, and that is the working with strings cheat sheet, right? So that one actually has a overview of all the different things you can do with strings. So it will tell you how to detect matches with string detect, string width, string locate, how to mutate them with sub, but you can also replace. You can take all kind of different subsets. You can join, you can split, you can check the length, right? So there's a lot of stuff you can do with strings, and it actually also has a pretty good explanations of regular expressions, which will be our next topic. So if you ever get confused about what you're supposed to do with strings, then the Stringer cheat sheet is a fantastic resource for you. Now, the string operations in Stringer that you saw before, like the subsetting, can be used for quite a number of things. The big problem is, of course, you need to know exactly from where to where you want to take the substring, right? So you need to know that the date starts at the first element and it ends until the 10th element. And this only works if the date is actually a constant size, right? So maybe in other date formations and other things you're looking for, you can't just say give me element 4 to element 7. Maybe you want to say give me the elements between some sort of other text and some other text, give me all the email addresses you can find me something that looks like a zip code. And there's lots of things that you would maybe want to extract or remove from a text, but that you can't really say, just give me the first to the fifth elements. So for this reason, regular expressions are a fantastic tool. Now, what are regular expressions? In a way, regular expressions are simply a way to express what you're looking for in a text. So they're a little sub-language to describe patterns. Now, that probably sounds very abstract, but let's show something very simple. So suppose that we have some example texts. This is pretty silly, but it says, hi, I'm Bob. My email address is bob@example.com, and we have a hashtag for millennials, because millennials love hashtags, right? So suppose we want to find anything resembling the word address. Let's first just look for literally the word address. What we can then do is say we're going to look for, using string view function here in the text, we're going to look for the word address. And then here, of course, it just simply found the word address. That's not very impressive. But we could also say we're looking for anything that starts with an A, and then has whatever, and then an S. And then it found email address is actually, because there's a little S here, and it found from the H from hashtag to the S for millennials. So this is a pattern I described, and it finds that pattern in the text. Now this is a relatively simple pattern, but using regular expressions you can make an enormously complex set of patterns, from looking for HTML tags, email addresses, zip codes, things that look like dates, basically anything that you can describe as a pattern in text you can find with regular expressions. And one of the fantastic things about regular expressions is you learn them now in the context of R. But regular expressions can actually be used in all kinds of languages. They can be used in Python, they can even be used in Excel, they can be used in C and Java, and whatever language you encounter, you can use regular expressions. So it is an extremely useful skill to learn, and it will probably allow you to solve a lot of tasks easily that would otherwise have seemed very difficult. Now, how do those patterns work? The first thing you saw is that if you have a literal text, it just matches that actual text, right? So the word address matches the word address. You can also say I would like to match any character, so you can also say I want to match an A and then 5 or whatever followed by an S, right? And then it still finds the address here. If you want to say I want anything following an A, so an A followed by something, and then it finds AI and it finds AS over here. So the little dot here means match whatever you can find. It will also happily match, say, a @ sign, right? So it doesn't have to be a letter, it can be anything that matches. So that is the point, the periods. If you actually want to match a literal period, like the one here in example.com, now if you would say I'm looking for .com, it will actually find this one, but it finds it because a period is also a character, right? But suppose we would have, I don't know, acom here, then it would also match acom because it matches anything followed by com. So what you want to do here is say, I didn't mean the period as a special character, I meant it as a regular character, in which case you have to escape it by prepending two backslashes. So \\\, period com actually means a literal period followed by the literal letter com, right? So period com, .com, which only matches the .com here. There are also some other things, like you could say I want to match only word characters. So you could say I'm looking for say an S followed by a word character, that's a W. So then it finds this S because it ends on, it has an S afterwards. It doesn't find this one because it's followed by a space, and a space is not a word character. And in fact, a word character is defined as anything from A to Z or 0 to 9, so letters and normal Western letters and numbers, and the underscore, interestingly enough, which sort of betrays its nerdy heritage. You can also flip it around by doing a capital W, which means anything except for a word character. And so in that case, you only find the S over here. Another thing you can do is create a so-called character class. So you can say, I'm looking for a capital B followed by either an O or an A or a U or a I or an E, right? So followed by a vowel basically. And then it finds the BO combination over here because these are one of these combinations. You could also say I'm looking for a S followed by either a word character or a space. And then it finds both the S over here, and it should have found my S over there. So you would expect it to now also find the S over here. The reason it doesn't do that because string view only gives you the first result for every element. So let's do a view all. And then we can see that indeed it matches an S followed by either another word character or an S followed by a space. And so between those square brackets, you can use any of these existing abbreviations in order to say define a selection of things that you would like to match. A final interesting one is the \b. The \b matches what they call a word boundary. So if you have matches b and \b followed by a, you only have a's at the beginning of a word. It could also be at the beginning of the whole text. So the M also matches the M for email here. If you flip it around, so if you say M followed by a word boundary, then we'll only find M's at the end of a word. So this is the M's here and the M at the end of the text over here. So what we've seen here is that you can type in literal letters, and actually every normal letter is just matches the literal letter that it says. So address matches address. The period matches anything. And if you want to have a literal period, you should have a backslash followed by a period. And in R, you have to double every backslash because R would otherwise interpret the backslash period itself, and you don't want R to interpret it, you want the regular expression to interpret it. So you need to also escape your backslash in a sense, so you always need to use double backslashes. So you do \\.com, that means a literal period followed by com. You can also match word characters. You can match everything except for word characters. There's also digits, that's \d, everything except for digits, \D. And you can make character classes using square brackets, and anything you put in the character class will be matched. And you can also use the shortcuts there. So this is an S followed by any word character or space. And finally, we've seen word boundaries, which matches on the boundary between a word character and a non-word character. In other words, it will match the beginning or end of words. Now, as I said above, the \w is actually sort of weird because it matches A to Z and 0 to 9 and an underscore, which made sense from a programming perspective because those are the things that you're allowed to put in variable labels. But if we're using with non-Western texts, you don't actually expect everything to be A to Z, etc. And the underscore really doesn't have so much place there. So a better thing to use in that case might be the so-called \p. And the \p uses Unicode properties. And for example, there's Unicode property for a letter. And the Unicode property for a letter, and let's use string view all here again, is any letter. Now in this case, it is more or less the same as a \w, right? So all these things are letters, but the letter will not match underscores, which is good, but it will also match any non-Western letters, right? So if you have Japanese text or Chinese text or Arabic text, this will still work because it uses Unicode properties, and the W might not work. There's a lot of these Unicode properties. For example, you also have a space. You can also detect only Arab language text, or you can detect only Chinese text based on the character encodings. If you want to learn more, just Google what is called Unicode properties, right? So Unicode properties are an extremely useful thing to go about, especially if you have non-Western text as well. Right, so what we looked at now is how to basically match single letters. But of course, most of the times we don't want to match single letters, right? We want to match multiple letters. For example, if we would want to make a small regular expression for an email address, we could want to build something like string view all text, and then let's say we want to say word characters, a bunch of them, followed by an @ sign, followed by a bunch more word characters, followed by an actual periods, followed by a bunch more word characters. And this matches the email address. And how it works is that after saying I have a word character, I specify how many word characters I'm looking for. And this uses the plus, which means one or more. And so plus means one or more. I could also use the asterisk, which means 0 or more. and you can use the question mark, which means 1 or 0, so an optional one, in which case it only matches little b here. For example, if you would like to match both the Dutch and the American English spelling of address, so with the double D or without the double D, you could say I'm looking for a single A followed by a 1 or more D's followed by an R and E and then 1 or more S's. Right, so that matches address with double D, double S. It would also match address with a single D and a single S. Suppose you would want to match both American and European color, you could say color, but the U is optional, right? So it can be either a U or not a U, right? 0 or 1 U's. You can also specify this more exactly. So you could say I'm looking for 0 to 1 U's. And then you could also say I'm looking for 3 to 7 U's, right? If that's what you're looking for. So there's 3 shortcuts. There's the plus, there's the asterisk, there is the question mark, and they mean 1 or more, 0 or more, or 0 or 1, so it is optional. And you can also specify exactly how many things you're looking for by using the curly braces like this. Now, using these building blocks, we can start building some email address. We already saw our email address detector, and I think it's this one over here. So this is a sort of reasonable approximation for an email address. Of course, it won't actually work for all of them because some people have more than one period here. Some people have more complicated things here. You can actually have accents in your email address, etc. We can try to deal with them. So we could say, for example, that there can be multiple periods here. So we can say this can be a word character or a period. And that would also match if we have a other email address. So let's actually make some. So suppose we have bob@example.com. We have bob@subdomain.example.com. In that case, our earlier email address won't actually work. So let's call this text. And so our first attempt would find the first one, but it wouldn't find the second one. It would stop at the .example, and we wanted to go on to the .com as well. This solves it by saying we do here before the period we accept everything that is either a word character or a period, but then of course it will also start matching illegal addresses. For example, it would match this address, which is not a legal address, right? But it would still match it because it contains words followed by an @ sign followed by either words or periods followed by period and words, right? So this doesn't actually work. It would also match something like bob@example. This is not a real address because it doesn't know anything about the top level domain. And of course, there again, you could say, well, I don't want any number of them. I just want like probably 2 to 4 of them, right? For info, org, NL, etc. But then, of course, they started selling longer addresses. So now you also have longer addresses. You already saw that this became more complicated. And actually, if you want an email regular expression that more or less works for most actual valid emails, you get at something like this monstrosity, right? So what I'm trying to say here is you can solve almost everything with regular expressions. Sometimes it gets really complicated real fast. However, a relatively simple expression like this one, which might look complicated but is quite readable if you get down to it, right? It says word character 1 or more, @ sign, word character 1 or more, periods, word character 1 or more, right? Which describes the structure of a typical email address. You can make it a little bit complicated, but it doesn't really don't really go overboard. Let's get you 2 more examples. So, for example, one of them could be there in our original text. It said, "Hi, I'm Bob, and my address is something." So let's find any I'm something. And so if people introduce themselves, want to know what their names are, then we're saying we're looking for the little string I'm, followed by a space, followed by word characters, followed by the end of the words. And so this matches, "Hi, I'm Bob." Finally, let's match some hashtags. These are pretty simple. You just say I want to match a literal @ sign followed by a bunch of word characters, right? And that matches these hashtags. Now in this case, I could have left out the escape because the hashtag doesn't actually mean anything in regular expressions. But anytime it is a head is not a normal letter, it's not an alphanumeric character, you're allowed to escape it in case you doubt whether you need to escape it or not. So now you know how to formulate a regular expression. You probably want to know how to actually use regular expressions, right? So for example, suppose we have those texts and maybe we have a table containing the text. So we have our data frame and it is a table, it has an ID 123 and it has a text column which is our original texts. Right, we have a little data frame like this, and now suppose we want to, for example, identify which of our data have a hashtag in them. So then we can say d filter, and what we want to filter by is whether there is a hashtag here, which is we use the string detect function for. So this detects a regular expression in a string. And in all the str functions, like all tidyverse functions, the first argument is actually the data you want to run it on. So the first thing is the string you want to run on, which in this case is text. And the second argument is the pattern. And the pattern in this case would be our little hashtag pattern. Right? So this identifies, this filters to find only text that contain hashtags. We'd also say I'm looking for text that contain email addresses, right? Using our simple email address regular expression we defined above. And this will find only those texts that contain an email address. So this can be a really useful way to quickly filter text or quickly identify texts that have not necessarily a specific subtext, but that contain a specific pattern. You can also negate it, so you can also say I'm looking for everything except for those, and then you simply say negate equals true, and then you find everything except for those that contain a hashtag. So if you know that you, for example, scraped some junk as well, you can throw away all the junk by throwing away everything that contains a certain pattern. Another thing you might want to do is to maybe get rid of hashtags. So you can say, and then of course we won't filter, but we'll mutate. So we will say mutate. Our text becomes the string replace all, and we want to replace all hashtags, for example, by an empty string. Right? So then the hashtags here are removed. We could do the same, of course, for email addresses. Yeah, you can remove everything you want. You could also say maybe we replace this by redacted, so that people know there was a name or an email address is there. So this is used to replace one sort of pattern that you find by another string that you define. If you want to remove strings, you can of course replace by an empty string, but because that is such a frequent use case, there's also a function remove all, which automatically replaces by an empty string. So this again removes all the hashtags. We could also have removed all the email addresses, or we could do something like we remove all the names, assuming that everything that starts with a capital is a name, and so then Bob is removed here because Bob starts with a capital followed by a number of letters. So you can use string detect to find patterns in your string and filter your data to get only those rows that contain or don't contain it. You can use replace all to replace all occurrences of a certain pattern by another substring. And you can use remove to actually get rid of all hashtags or all email addresses or all names or all whatever you can define. Finally, there's a very useful function called string extract. So let's say we are looking for addresses. We could say string extract. From the text, we want to find the email address. So we again use our stupid little email address here. And then you'll see that and if it didn't occur, you get a missing value. And if it did occur, you get the first email address here. You can also do extract all. The problem there, of course, is that because it is vectorized over the text, then you would get a text that sometimes contains 0 values, sometimes contains 1 value. If you're looking for a hashtag, it would here contain 2 values. So that's a little bit more complicated. And then the end results will actually be a, what did I do wrong? A bracket too much. And this should have been d.text. And then the end result is actually a list that can contain a varying number of strings, so it's now no longer a neat little column, right? So this is a little bit more complicated, but if this is what you want to do, so for example, you need to gather all the hashtags, then you can do so using the extract all function. Right, so if you it looks like very simple building blocks, right? There's these little regular expressions that you can build, and there's functions like detect and replace and remove and extract. But really a lot of typical use cases like finding all addresses, replacing certain junk, getting rid of HTML entities. A lot of these sort of use cases can be dealt with by using regular expressions. So it really is worth your time to learn about regular expressions. And of course, to learn more about this, there's tons of material on the internet, including the cheat sheet I showed you a second ago. And there's also a section on regular expressions in our upcoming book on computational social science. The final thing I want to talk about today is the issue of character encodings. This is actually a pretty difficult topic, which I could talk about for a longer period, but I just want to give you the basics so that you can at least understand what's happening and diagnose the most common problems. So what is a character encoding? In a sense, if you store a piece of text in the computer, stored in memory, it looks like an A, but as you probably know, computer memory consists simply out of zeros or ones. It consists out of numbers, so it needs to encode the A into a sequence of zeros and ones that we recognize as a number. And you can actually find out what the encoding is by using the character raw function. And so a small case A is number 61. A small case Z would be number 7A, right? So this is in hexadecimal numbers. This is 7A, and the one that we all know that this is the 65, right? And in hexadecimal notation, that is 41. Now the actual number is not really that important, but what you see is that all these numbers are represented as a number between 0 and 255, and they're stored in 1 byte. This all used to be fairly simple, and of course computers have to agree on this, right? So you would hope that my computer knows that 41 means an A and that your computer agrees with it. And that used to be fairly okay when most computer users either were from English-speaking countries, or they used English and they only used Latin letters. But it became a lot more complicated when people also started using other letters, right? So the first challenge was probably when they had to deal with things like an accent. So there's an A with a little with an acute accent on it. And what you see here, that this is actually no longer represented by a single byte. This is represented by 2 bytes. Now that still seems fine, right? There's plenty of bytes in the computer, so we can use 2 to represent the letter here. But where it gets complicated is that although all computers more or less in the world agree that 41 means a capital A, there are multiple ways to actually encode other characters like accented characters, and especially also characters like Chinese characters, right? So if we take a Chinese or kanji character here, you can see this is represented by 3 bytes, but how this is represented actually depends on what we call the encoding. Now you might have heard of something called ASCII. The ASCII or the ANSI is the more or less default encoding that was used until people started noticing cultures and languages other than the English one. And then they had to invent new ways to actually encode all these things. And the first thing that happened is they didn't want to waste any space. We're talking now about like the 70s and 80s, where computer memory was still really expensive. So they never would want to spend 2 bytes representing a single character. So they invented different encodings for Western European accent, but also for Greek and for Russian. And they invented encodings for all these different languages. And so an A with an accent in a Greek encoding might actually be a Cyrillic character in another encoding. This became even more complicated when we started dealing with non-Western alphabets, and especially, of course, when we had to deal with Chinese and Japanese characters, because there's not like a couple of them, there's literally tens of thousands of them, or hundreds of thousands. So it was really a really big mess until they formed what is called the Unicode Consortium, and probably people know, if they know about Unicode, they know because at some point they decided to standardize emoji, and all of a sudden everybody became interested in Unicode because everybody likes their emoticons or the emoji. However, what Unicode really did for us, it standardized the number used for every character, right? So there's only one Unicode encoding for every type of character you can imagine, and this goes for Latin letters, this goes for Chinese, for Arabic, it even goes for fantasy scripts like Klingon and runic Tolkien runes. It goes for languages that we don't use anymore, like Viking languages. So basically every language we've ever heard of, and now including emoji, is has a standard representation in Unicode. So that sounds good, right? However, there's one little problem, and namely there's not one standardized way to encode Unicode. So even if you agree on what the number should be for a character, you can still encode it in multiple ways. Yeah? And a function to deal with this is the conversion function. So we could say I'd like to convert this character to UTF-8, which is actually probably the standard encoding on my computer, because I have a Western computer. This might be different on a different computer. But the conversion of this to UTF-8 actually looks like this. Let's car2raw it again. And then you see that in UTF-8, the Chinese character is encoded in 3 bytes, while in UTF-8, the Western characters are all encoded as a single byte. Now that sort of makes sense, right? Because there's so many more Chinese characters, you actually need to use more bytes to encode them. But still, it is more efficient if you are dealing with a lot of Chinese text to actually encode it using a encoding that is tailored towards Chinese, like for example the GB2312 encoding, which only encodes this using 2 bytes, right? So this is more efficient for Chinese characters, but it might be less efficient for some Western characters. I'm not quite sure how this converts this one. Alright, so for this one it's still fine. You can see it's different from the conversion in encoding in Unicode, but it's still only 2 bytes. Now, what of all of this you actually need to remember? One thing you should probably remember is that if you ever have a choice, please use UTF-8 unless you have a really, really good reason for using anything else. UTF-8 can encode all Unicode characters. It's reasonably efficient with Latin scripts, and it can also encode Chinese scripts. So UTF-8 probably should be your default encoding. The second thing to remember is that whenever you see weird stuff happening, like if you see an apostrophe replaced by 2 weird characters or something, if it doesn't display Japanese text correctly, whatever, it's probably an encoding problem. And encoding problems should almost always be solved at the source, at the point you're reading it in. So suppose you are using readtext to read a file. I have a file called text.txt, which actually contains some Japanese text in there. And what you see here is that it will have encoded it and actually decoded it, and this looks pretty correct here because it was encoded as UTF-8. But if you want to, you can specify explicitly the encoding. So if something ever goes wrong here, if you see that something goes wrong with accented characters or with apostrophes, there's a good chance there's something wrong with the encoding, and it might just pay to try out a couple encodings here. And the really important thing to remember is if you at any later point encounter a problem, it really pays to just go back to wherever the text entered your code the first time and make sure you immediately get the encoding correctly. The same in read CSV. You can specify the encoding through the locale. So you can say I want a UTF-8 encoded locale, and then you make explicit that you want to read this CSV file using UTF-8 encoding. And of course, if you have a Chinese text, you could also say I would like to read this in Chinese encoding. Now in this case, it actually tells us there's invalid inputs, it is invalid Chinese encoding there. We could also see what happens if you would use a Latin 1 encoding, which is the better name for the ISO the ISO 8859 encoding. So if we would use that in R, we could use the ISO encoding here. So let's see what happens if we would read this as ISO encoding. And there you actually see it's really completely mangled, right? The text here doesn't look like anything anymore. And the reason that's happening, so you see these kind of weird accented characters, that can be a very clear sign that something went wrong with encoding. Now, if all of your text is replaced by these kind of accented characters, it probably means that maybe it was encoded as GB2312 and you decoded this at UTF-8, or it was encoded, like in this case, as UTF-8, and you decoded it using Latin 1. But very often you'll see a lot of normal text, and then only a couple of them will be replaced by accented characters, very often like the apostrophes or the accents in the text. And in that case, it's probably a confusion between UTF-8 and Latin 1. Now again, the important thing here is not to be a guru with these encodings. The most important thing is to recognize when something might be an encoding problem, and to realize that the place that you want to solve this is actually at the point where the text enters your R code. So the read text or read CSV or whatever you use to read your text files. Finally, if you really don't know, there's something called guess encoding. So you can say, well, I don't know what encoding it is, so can you have a look please? And then it will look for certain markers and it will tell you, well, this is probably UTF-8 encoded with a confidence of 1. And otherwise it might be Windows encoded or COI8R encoded, whatever that means, right? So if you don't know how it's encoded, you could use the guess encoding function, and on longer text it's usually correct, because there's telltale signs for most of these encodings. Now again, this is a very short Unicode introduction. There's lots more to learn here, but the important thing is to understand how text is represented on the memory and on your file. That Unicode can be encoded in different ways, and that especially you need to specify the encoding when you are reading the text if something is going wrong. And whenever you have a choice, just use the UTF-8 format, because that's the most universally expected format, and it's also a fairly efficient format. Right. Good luck with this, especially with the regular expressions. Start playing around with it, right? If you have any data, see if you can make some cool patterns, like try to identify fields or email addresses or zip codes or whatever you can think of in your text. See if you can make a regular expression that captures that specific pattern. This can be lots of fun. There's actually web pages devoted to making regular expression challenges where you can test your regular expression skills. But the most important thing is, if you become confident with regular expressions, you have learned a really useful sub-language that can be used in R, but you can also use it in Python, in Java, and any programming language allows you to use regular expressions, and they can be used to identify text, to replace text, to extract text. And so it's an extremely versatile tool, and it's well worth spending some time learning. Good luck!